The first video lab report consisted of filming any object moving to later analyze the motion. I filmed a pool ball moving from one side of the table to the other. What was my prediction on the ball's motion? Constant motion. In a context with ideal conditions, no external forces acted on the ball, yielding a net force of 0. You will see I explain this statement in further detail and with more clarity as this video goes on. The ball's motion was analyzed and compared with a computer model that predicts the ball's motion based on an adapted version of Newton's second law. Newton's second law states that the acceleration in a system depends on the system's mass and the sum of the forces acting on the system. Let's start by looking at the analysis done on Tracker. The first thing I would like to point out is the fact that the pool ball looks somehow blurry. Although I tried many times to eliminate the blurriness, the place slide did not let me. The first important data is the average diameter of a pool ball, 0.057 meters, used to establish a calibration stick. Here is the calibration stick. Although the ball's circumference looks blurry, I pointed out its average point of mass at each frame so that Tracker could calculate the ball's position and the time at such position, everything based in the assigned orientation of the axis. As you can see, I pointed the origin to be at the ball's center, based on the first frame. The positive x-axis is located at the right of the origin, and the positive y-axis at the top of the origin. If for any reason I decided to choose a different orientation in the two axes, only the sign of each position value could have changed. By this I mean that if the origin was the same and the orientation different, positive values could have become negative and vice versa, yet they would have been the same numbers. If I decided to place the origin of the axis in a whole different place, then all the position values would have completely changed. Let's now take a look at the video and at the data thrown out by Tracker. Consider that the point of mass at each frame is what throws this data. As you can see here, the values of position versus time show that the ball started to slow down towards the end of the video. This means that the change in position started to be smaller as time passed. What is the physical explanation to this? Well, there is a force to consider in pool tables, the force of friction. The surface in a pool table causes some amount of friction that causes the ball to slow down, because the magnitude and direction of such force acting on the system, the ball, are opposite to the object's direction. For the computational model, it is assumed that the net force acting on the system is equal to 0. This means no external forces affecting the ball's motion. It is not possible to determine how many pushes and pulls are included in the net force, and they cannot be measured either. Again, for this experiment, the sum of pushes and pulls is equal to 0. If we now take our adapted form of Newton's second law and insert 0 for the net force, we can see that the final velocity is equal to the initial velocity plus 0, constant velocity. This is the initial equation from Newton's second law. This is the adapted equation for Newton's second law. And this is constant velocity. Final velocity equals initial velocity. The question now is, how do we calculate the initial velocity of the pool ball? I picked up the first time and the first position and the second time and the second position registered in Tracker, and based on the formula for average velocity, I calculated the initial velocity that would keep constant in our model. Let's now take a look at the computational model with the information I mentioned inserted on it. Knowing the ball's initial velocity, the ball's initial position on X, a pool ball's average mass 0.16 kilograms, last frame's time 1.12 seconds, and the fact that the net force is equal to 0, I was finally able to insert the crucial values into Python's code to create the computational model. As you will see right now, the model actually predicts constant motion. The graph produced shows this. After analyzing the ball's motion on Tracker and creating a computational model for the system, these two were compared. This plot shows the comparison between the two. As you can see here, the dots represent the analysis in Tracker, and the straight line represents the computational model. They are very similar, but as I mentioned earlier, it can be seen that the pool ball started to slow down at the end of the video. Concluding, the computational model was able to generally predict the pool ball's motion. As I mentioned at the beginning, this experiment was based on the idea that ideal conditions yield a net force equal to zero. If there is no external force, the system moves in constant motion, which is pretty much what the ball does in this case. The observations and the predictions, Tracker and Python, show a similar behavior,